prepared sample of a radioactive isotope X containing 1.8 times 10 to the 15 atoms of the isotope. The half-life of the isotope is 8 hours, and we've got to calculate, part C, so we've got to calculate the energy transfer from the sample in 24 hours if the isotope emits alpha particles of energy 5 mega electron volts. Alright, so let's jump across. And the scenario we're actually working with is that we've got some form of source, and we're interested in the time of 24 hours that it's going to be emitting alpha radiation, and it says that each alpha decay emits 5 times 10 to the 6 electron volts, so 5 mega electron volts. Now, to work out the total energy it emits, so the total energy is going to be the number of decays, or the number of emissions of alpha, or however you think of it, times by the energy of each. Okay. So, they've given us the energy of each decay. So here we know 5 times 10 to the 6 electron volts. But the question is, how many decays were there in this source within 24 hours? Now, actually, they got you to work this out before. So in 2BII, you actually worked out that 24 hours, there were 15.8 times 10 to the 14 decays. So, therefore, over 24 hours, you've got 15.8 times 10 to the 14 nuclei decaying, each giving out 5 times 10 to the 6 electron volts. So we can plug those numbers into a calculator to work out the total energy emitted within that 24 hours. So we've got 15.8 times 10 to the 14 times by 5e to the 6 gives me 7.9 times 10 to the 21, and we're working in electron volts, remember. So we've got electron volts at the moment. Now, having had a quick look, I can see that what they actually want is an answer in joules, which is not unusual, and you should be familiar converting between the two. So if we look at it then, we know the energy is charge times by the potential difference. Now the charge on an electron is 1.60 times 10 to the minus 19 coulombs, and going up 1 volt in an electron volt, so that we know that that gives us 1.60 times 10 to the minus 19 joules is equal to 1 electron volt. Because it's 1 electron gone up by 1 volt. Therefore, the energy emitted in joules is going to be 7.9 times 10 to the 21 electron volts. And each of them is worth 1.60 times 10 to the minus 19 joules, meaning that in total we emit, plugging the numbers into the calculator, 1.6e to the minus 19 times by 7.9 times 10 to the 21 gives us an answer of 1264 joules. Now if you look back, 3 significant figures, 2 significant figures. To be honest, they've only given us 1 significant figure here, so I don't think they want an answer to 1 significant figure. I'm going to give them 2 significant figures, so in theory I should give them 1 significant figure answer. So I can actually say the answer was 1300 joules to 2 significant figures, though it's actually factually incorrect because they've only given me 1 significant figure there. Hope that helps. Thank you very much.